if I can find it. Got it in my email here somewhere. Let's see, where am I at here? Let's see here.
Yeah. That's the best spike one we got.
I haven't tried the other one.
It's too plain.
Okay.
Yeah, pulls out into his alcohol. The one he did since it's called Mountain Spike.
Where's the homework? Oh, here we go. No, that's not it.
Okay.
Okay. So those of you who do not know what the homework is, I'm going to tell you what the homework is. If I can get it here. Where is it? There we go. For chapter 13, let's see, in section 13.2, let's see, I'm not figuring it out here really quick. There we go. 13.2. Okay. Sorry, I'm very tired. Packer and I just spent a whole day in a greenhouse at 130 degrees. So it's a little, my body's a little burnt out. Okay, in 13.2, we did Eiffel Tower. No, is that right?
Yep. Yeah. We just modified.
Oh, we did the Eiffel Tower, except you have to choose another famous building in the world
Of your choice.
of your choice, made of steel.
And you
Right.
act like it's completely made of steel.
Yeah. Okay. Then the second one we did is the expansion gap problem, right?
Which one?
The expansion gap on a steel railroad rail. Except instead of being 10 meters long, how long did we make them?
120 meters.
We made them 120 meters long. So, so if you go to 13.2 in the book, go to 13.2 in the book. At the end of at the end of the section, we're doing the Eiffel Tower problem. Choose your own building. Got to figure out the expansion of your own building. Then we're doing the steel railroad rails problem, and we're using rails that are 120 meters long instead of 10 meters long. And then, did we do any others?
For 13.2.
Yeah, oh yeah, we did.
Density of water and pressure one.
Yes, the density of water and the pressure one. So that's the second to last problem. The density of water at 0 degrees is very nearly 1,000 kilograms per meter cubed. So do you got those? 3 problems in 13.2? Oh man, I need some water.
If you bring different tabs in this class, we guarantee
All right. Did you get those, Leslie? Section 3.2. The Eiffel Tower problem, the railroad rail problem, and the expanding water problem, which is the second to last problem. Got those? Okay. 13.3, we did let's see, what did we do?
Tire pressure one.
Tire pressure one.
Except you changed a couple things.
We changed tire pressure one. We changed to 45 psi at 70 degrees Fahrenheit, and we wanted to know the pressure at negative 10 degrees Fahrenheit.
Is it alright if you use pounds per square inch, or do we need to convert the PSI?
Pounds per square inch is psi. Oh, you mean
You
convert it?
need to convert it from.
I didn't specify, so I don't really care.
Okay.
You definitely need to convert it if you're going to be using any constants that have specific values that you use. So, besides that, well, for example, the ideal gas law constant has specific units to it. So when you're using the ideal gas law, you have to use either atmosphere and Kelvin or Pascal and Kelvin, because it's designed for those. So 13.3, the second one we did is, I can't tell which one the second one is. What is the second one?
The helium filled balloon law.
The helium balloon?
Yeah.
Okay, I believe you. Did we change anything there?
Sea level with temperature of 30 degrees Celsius. Go to altitude with temperature is negative 40 degrees Celsius. Volume still 20 times. Is what I wrote down.
So we changed the altitudes and the temperature. We went from sea level at 30 degrees Celsius to what?
To the altitude where temperature is negative 40 degrees Celsius.
To the altitude where temperature is negative 40 degrees Celsius. And we figured out the new
Volume
pressure.
is still 20 times.
The volume is going to change by 20 times, so there's a nice little change of state problem. That was the next one. And then 13.3, also we did density of, what's the next one?
Airplane. The airplane passenger.
Airplane passenger.
Kind of right in the middle. More towards the top and the bottom. Or actually closer to the top.
Okay, let's see here.
Which one is the airplane passenger? This was for 13.3.
Okay, I'm going to have to believe you on that one.
We changed the volume of air in the stomach is 75 centimeters cubed, not 100.
My book hasn't changed yet. Hold on. It says that my internet connection is unstable. I've told them 100 times to connect this hardwire to the wall. But they just won't listen to me and they can't do it. Okay. Wait, what's your we're in 13.4, aren't we? 13.3 still?
Yeah, there's the
Oh.
one about the airplane passenger.
No wonder I couldn't find it. It was in the wrong one. 13.3, airplane passenger. Where's my airplane passenger?
It's the,
Ah, yes.
and then you change the volume of air in the stomach to 75 centimeters cubed.
So the volume of the air in the stomach before the plane takes off is now going to be 75 centimeters cubed. And the cruising altitude, we want to figure out what's going to happen. All right? Okay. And that's it for this one, right?
I think I had it down on
What was the last one you had?
there was the 3 more down, the number density of gas atoms.
The number density of gas. Remember, number density is a number per volume, an amount per volume. So it's the number density problem. Give you a little bit of a challenge there. Find the number of the number density of gas atoms. That one at a certain location in space. Yeah. Then you're going to calculate the temperature with that many atoms and that pressure.
And I think you wanted us to calculate the temperature at all 3 Celsius, Fahrenheit, and Kelvin.
Calculate the temperature in Celsius, Fahrenheit, and Kelvin. Okay. All right, good. So then 13.4. So in 13.4, what's the first problem we did?
Average molecular speeds for 3 gases of my choice. I don't know if that was a problem based off what went down there, if you just wanted us to do that.
Average atomic and molecular speeds, yes. And we didn't change that one.
Yep, you just wanted us to do it for 3 gases of our choice.
And then the escape velocity, so the average atomic molecular speed for gases, 3 gases of your choice. And then we did we do the escape velocity next?
Yeah, for oxygen.
The escape velocity of oxygen, that's the third problem down. Then what? What did we do after that?
Nuclear fusion for the sun.
Nuclear fusion. We just skipped every other one, huh? Nuclear fusion for the sun.
Which is
Oh.
just the next problem down.
Yeah.
And that was all I had written down for 13.
That's 13.4. Okay. Now, 13.5. It's all about phase changes. We did our triple point, right?
Yep.
Very fun. Talked about phase diagrams and other things. I'm not going to go into this stuff, and there's not really any homework to do. And I'm not going to go into humidity evaporation and boiling really either. We talked about that already. So
So we don't have any.
no homework there. The homework's done for chapter 13. And then chapter 14 we got into. We started this, didn't we?
Yeah, we have chapter homework for chapter 15, at least a little bit of it.
You gave us 7 questions.
7 questions in chapter 14.
hmm
Any in chapter 14.1?
Not
No.
bad.
Just 14.2 we started at?
Yep.
Okay, 14.2. Which questions did we do?
You wanted us to calculate the specific heat of a pure material.
Specific heat of a pure material. Which one was that?
It's the, it's in kind of that fourth section with the bars.
Should be towards the top.
Yeah, point.
Oh, I see.
25 kilograms.
So the 0.250 kilogram block of pure material? Okay. So you're doing that problem right there. The 0.25 kilogram block of pure material is heated from 20 degrees to 65, adding energy, and we're going to calculate the specific heat and identify the substance of which it is most likely composed.
And the 4.35 kilojoules would just be 4,350 joules, right?
That's correct. And then what's the next one we did?
Kilocalories in food.
Kilocalories in food. Find the number of kilocalories in food determined by calorimetry techniques. Okay. And remember, for the heat equations, we do have different constants. One constant that is used for calculating in joules, one for calculating in calories, in kilocalories, I think. But you can also just use one and convert to the other. So it just depends on how you want to do that.
Then we went to 14.3.
That's it for this one?
Mhm.
Yep. Sunny day swimming pool.
Okay, my computer's taking its time, apparently.
So is mine. Oh, there we go.
My piece of paper is completely
Okay, the swimming pool. This swimming pool. Swimming pool on a certain sunny day. The swimming pool's temperature would rise if not for evaporation. So you're using the latent heat of vaporization to calculate how much heat leaves a pool so that it won't rise that temperature. Essentially, you're equating the amount of heat necessary to increase the temperature, and you're equating that to the amount of heat required to vaporize a certain amount of mass of water, and you're calculating that mass of water that's going to vaporize, right?
So we're taking the amount of heat that should be going to warm it up.
Instead, it evaporates, solve for the mass, then you're going to calculate a percentage.
Okay.
Correct.
And then the
I
other
could
one-
just take a nap right now. What else did we do here?
There was one that was about a 1986 gargantuan iceberg.
The gargantuan iceberg.
Yeah.
Now they would say ginormous or something like that. Anyway. So, it's like the size of Rhode Island. Anyway, so that's the gargantuan iceberg problem. What else did we do?
14.5 fire walker.
We skipped 14.4,
Yep.
went to 14.5, and that's the last section we did, right?
Well, we have a couple. We have one for 14.6 and one for 14.7.
Oh. So the firework walker problem is the only one in this one?
Yep, that's what I have.
Fire walker runs across a bed of hot coals with lots of steam and burns. That's 14.5 problem. We didn't change any of these because I started to discover that they don't show solutions on all of these problems, so we're good. What do we do in 14.6? Looks like we're heating a cauldron with
Or coffee pot.
the coffee pot problem. And there should be videos for these. I'm not sure if I got them for all of them, but I think I did. A glass coffee pot with a circular bottom.
Yeah.
Yeah.
Okay.
What did you mean there should be videos for these?
Sorry?
You said something about videos?
Oh, the recorded videos for the lectures.
Okay, gotcha.
So what
And then the radiation one, we did a problem using the temperature and
our radiator.
the car radiator. Calculate the rate of heat transfer by radiation from a car radiator at 110 degrees Celsius to a 50 degrees Celsius environment. So there you go.
And you've given us one problem for 15.2.
And then we'd only done one problem for 15.2, you said. What was the problem in 15.2 we did?
It was about a fire pump.
And driven pump.
Ah, the tire pump. We did the tire pump problem in 15.2.
And then did we get 15.3 electrical power station problem?
We did that one.
I thought that's what I've written down.
15.3, we did the electrical power station problem. Apparently.
Is that one the
Sounds familiar. Because we talked about the fact that it's, so this one is the turbines at a coal-powered power plant. Improvement of efficiency to 3.32%. Is that the right one? Oh, no. It's the one above it. How much heat transfer occurs to the environment by an electrical power station that uses 1.25 times 10 to the 14 and has an efficiency of 42%. So it's the top one. How much heat transfer occurs? Okay, does anybody have any questions about what the homework is so far for chapters 13, 14, and 15?
Might have some more questions tomorrow.
Okay, we're going to continue finishing up chapter 15 here, and then we're going to move on to 16 today, and then finish up 16 and 17 tomorrow, and then we'll be done with the class. This week is the last week.
What are we doing on Wednesday?
Wednesday, hopefully we'll have enough time to do a lab.
The Martian lab, right?
No, we're gonna do waves. Waves on strings. It's kind of an important one. Okay, so we talked about Carnot's perfect heat engine a bit. And the Carnot cycle, we talked about his heat engine with the little drinking bird toy, right? Oh, you want the screen on? Okay, go ahead. So, you'll realize that we're moving rather quickly, but you'll find it's not terribly difficult to get through this stuff. It's not really as challenging as other stuff has been to date. But the efficiency of an engine is defined in this way. You have the heat that is leaving the hot side of the engine, that's coming into the hot side of the engine. Subtract off the heat that's leaving on the cool side of the engine, and divide it by the heat coming in on the hot side. You can simplify this to 1 minus QC over QH, and for the Carnot cycle, QC over QH equals TC over TH because of what the Carnot cycle is. The Carnot cycle has two isothermal curves and two adiabatic curves. So one is an isothermal, you lose pressure in this first isothermal. You go from a high pressure up here down to a low pressure, and you go from a low volume to a high volume. So this is called an isothermal expansion because it goes from a low volume to a high volume. And then you have an adiabatic expansion going even to a higher volume. And then you have a compression, an isothermal compression and an adiabatic compression. And this is the Carnot cycle. This is the ideal engine. It can't get any more efficient than this. And that is absolutely proven. It's proven that you can, because what is the efficiency of an engine? The efficiency of an engine is the total energy in, which is all of the area underneath the top two curves. And then you subtract off all of the area under the bottom two curves, and that will give you your total efficiency if you divide the two. Because the top, well, so mathematically it can be calculated what is the most efficient. And this turns out this is the most efficient engine that can be made in reality. Yes.
Still it's not.
Screen doesn't. Get a ruler there and push the red button. See if it works then. If you guys were my basketball players from a couple of years ago, you could reach it almost without standing up. I had a basketball player in here who was 6'8" or 6'9". Oh, that didn't work.
Should I try it again?
What's it doing? Blinking?
It's blinking red under the power.
I don't know what that means. Alright, let me try to turn it on again from up here. It's blinking up here too. I don't know what that means. Blinky. Blinky the projector. We'll call him. There. Let's see. I wish I could just hit it with a baseball bat like a pinata. Okay, I don't apparently I don't have a projector in their room right now. So we're gonna have to go with the old school version of things. The whiteboard.
Yay.
Alright. So the Carnot cycle looks like this. Ouch. With your volume here and your pressure here. You've got isothermal expansion going from this volume to this volume. It's expanding, and then you have an adiabatic expansion going from this volume out to this volume. And then you have an isothermal compression from here to here, and an adiabatic compression going from there to there. And mathematically speaking, this has been proven to create the smallest difference in area underneath these top two curves. If you calculate the area under those two curves, and then subtract the area underneath these two lower curves, then you're going to get essentially the area in between all the curves. If you do that difference, because whenever you're calculating the area under these curves, you're calculating the energy essentially. So if you calculate the difference in the energy, then you're going to get the total energy used by that curve, and then you can put that's essentially the work done. Then you can put that over the total energy and get the efficiency. The work done over the total energy is the definition of efficiency. So what you really want to do is you want to essentially make this area under the curve as small as possible, this area down here, as small as possible, so that you do as much work as possible for the total amount of energy you have. Or in other words, you want to get this area as big as possible. And it can be done using calculus. You know, to maximize an area, you take maximize the area between curves. You do some integrals, differences of functions and inner rule and everything else, but in the end you can calculate exactly what is going to be the peak, the biggest efficiency, and this is it. For an engine that can be done with great difficulty and a lot of careful work, it's as good as it gets. And so it turns out that efficiency has a ceiling to it. You can only get to a certain efficiency, and that's the efficiency of the Carnot, and I guarantee you it's not 100%, it's nowhere close. It's more like in the 60s, close to 70%.
What do most car engines operate at?
Most Carnot engines operate somewhere in the 60%.
Most car engines.
Oh, car engines are more like the 40%-ish.
Is
So,
that just like regular ones, or what?
good ones today, probably in the 40s. Car engines are not a Carnot cycle, but they're not terrible, but they're not great either. And they're working on making them more and more efficient. One of the ways that you make them efficient is help them to radiate heat more, so that the cool side of the engine is cooler. And so you get a bigger heat difference, a bigger temperature difference across the engine. Another thing that you can do is to create a better cooling system. Fewer leaks in the engine, of course, so you want less expansion in the engine as it gets hot so that it doesn't leak. There's lots of different things you can do to improve the efficiency of an engine, but you can only go so far, and then you start running into the Carnot wall of efficiency. And then here they treat the nuclear reactor as a Carnot engine, and they calculate this efficiency of a Carnot engine that's at 573 Kelvin at one end and 300 at the other, at the hot end and the cold end. So if it's at 300 and 573 Kelvin, then you get 47.6 efficiency.
That's better than full, right?
Well, yeah, because that's calculating the Carnot efficiency right there. So this is the this is the hottest temperature you can reach with a nuclear power plant, and the hottest temperature above room temperature. So that's essentially the best efficiency you can possibly get with a nuclear power plant operating between those two temperatures. But what they actually get is about 35%. It turns out actually coal, oil, and natural gas are actually greater efficiencies. They're about 42%, and the reason is because their temperatures can go higher. A nuclear power plant can't go any higher without losing containment.
Without having a meltdown or
Yeah,
something.
starting problems. So, but you can go higher with coal and natural gas. So anyway, see, we didn't give any homework in this section, did we?
I don't think so, not yet.
Let's do the steam locomotives one. So where it says steam locomotives have an efficiency of 17% and operate with a hot steam temperature of 425 degrees Celsius. So that's the first one we'll do. And let's do a gas-cooled nuclear reactor one as well. That's above that one, so it's the second problem. We'll do those two for now. And we'll move on to the next section. So now we've talked about Carnot's heat engine, which takes heat from a hot reservoir, does some work, applies a force and causes some movement, and then it has heat that goes out of it into the cool side, the cool reservoir. And there's some equations about the efficiency and the stuff that can be done there, the work to be done and all that. But what happens if instead of drawing heat from a hot reservoir, doing some work and then dumping our waste heat into the cool reservoir, what if we draw heat from a cool reservoir by doing some work? We talked about this already. What do we call that?
Refrigeration.
We call it refrigeration. I think we must have lost our meeting here.
Probably happened when we turned the screen on.
Are you still there, Cassidy? Fair enough. Sorry, Cassidy, did we lose you there?
Yeah, I have a lot of family at my house right now, so my internet's kind of.
Oh, I see. Where did we lose? When did we lose you? What part of the discussion?
I don't even know. It was cutting out really bad.
Okay. Let's see here.
But it's okay. If you have it recorded, I can go back.
Okay, so it is being recorded. So we're now starting section 15.5, refrigerators. So what happens when we, instead of taking heat from the hot reservoir, doing some work and dumping the waste heat into the cool reservoir, what happens if we go backwards? If we take heat from a cold place by doing some work and then dumping it into a hot place, we call that refrigeration or air conditioning or something like that. And people have a hard time wrapping their head around this a lot, so we're going to try to figure out how it works. This is how it works in a very simple diagram. We have a cold place. If this is an air conditioner, if this circle is an air conditioner, this cold place is going to be inside the house. So this blue place is the place that you're trying to cool off. That's the inside of your house. Or it's the inside of your refrigerator. Then this circle is a kind of a machine that actually does work.
Circle, yes.
The circle here in the middle. Oh, sorry. This is on the very first part of 16.5. Our diagram looks like this. I forgot we were doing whiteboard teaching again. So the diagram looks like this. It has this blue place down here. Then it has a yellow place in the middle, which I'm going to color green. There's a circle. And it has an arrow going in with work going in. And this is the cold reservoir down here at the bottom. The bottom is the cold reservoir. They label that temperature cold. And it has heat leaving it, because usually the heat gets dumped into the cold reservoir. But now the heat is leaving this. This is still Q cold, but now the heat is going into our machine. And then we dump the heat out on the hot reservoir side that has the temperature hot. We dump that, that's outside the house. The red side is outside the house. This green here is the machine that does the work. And then this is our cold reservoir. So this is inside our house, this is the air conditioner, this is outside the house. And what kind of work does the air conditioner to do then? Well, in a power plant, when we're going backwards, when we're taking our heat from here to here, the heat that's brought in does work on this machine and creates electricity, turns the turbines, right? In this case, and what happens is you have high pressure gas that's hot that becomes low pressure gas and turns the turbines and becomes cooler, right? In this case, we're going to take some air that is cold and it's at low pressure because it's inside of a cold environment, and we're going to increase its pressure using this machine. So we're going to actually use a pump to compress it, okay? And then when we compress it, we're going to put it outside and allow it to evaporate. And when it does that, it loses energy. And then we can, when it loses energy, we can bring it back in as a gas. Now the problem is that we can't just use the air from inside the house to do this, because air doesn't compress very well down to a liquid. It takes a lot of pump power to do that. So we use something called Freon, which is a molecular liquid. It's like an alcohol kind of thing, and it evaporates very readily. It compresses very easily into a liquid again. So we can take the Freon and run our air from inside the house that's cold, but it's not so cold that it can't evaporate Freon. So we bring that in here and the Freon will, it's not so cold that the Freon won't absorb energy from it. That's a better way to say it. So we bring in the cold air from our house and we bring it close to the Freon, and the Freon absorbs some of the heat from it. And then we compress that Freon and we push it out here to the outside, and then it evaporates and it loses that heat we put into it. We bring it back in here and it comes back in as a gas, and we compress it again, and then we allow it to soak up some heat. We compress it again, send it outside. So we're compressing air using that work that goes into the air conditioner. And that's why air conditioner uses electricity, because it has to compress this Freon after it's been let off to outside and evaporated in the hot air outside to release all that heat that it has absorbed in the house. And just like with heat engines, you have a cycle. Except in this cycle, you're going backwards. Remember, in the engine cycle, we were going clockwise. And every cycle, we expanded a piston to do some work. And then we had to compress the piston again. We had to reset it so that we could get back to where we started, so we could go around this cycle. But in the refrigeration cycle, we go back the other direction. We go back the other direction. And we allow energy to be taken from the house to the outside and released by evaporative cooling. And then after that evaporative cooling happens, we have our freon turning into a gas, we recompress it, we reabsorb energy, and we do that cycle. And the ideal cycle, again, is the Carnot cycle. So the best efficiency you can get is with the Carnot cycle of adiabatic curves and isothermal curves.
So if I understand it correctly, what we're doing is the freon is absorbing the heat energy from the house and then taking it and putting it outside.
That's right. Liquid freon is being, the air in your house is being run over liquid tubes full of liquid freon. Okay? And then that liquid freon absorbs, because liquid freon is pretty cold when it's compressed. So it absorbs energy from the air that's warmer than the liquid freon, even though the air is coming from an air-conditioned house. It's not necessarily that warm. Liquid freon is much colder when it's compressed.
Okay.
So then we take that liquid freon that has now been warmed up from its normal liquid state, and we pump it outside and we let it expand. There's an expansion valve that allows it to expand into many channels instead of one. So inside the house, it takes up little space because it's a liquid. But once we get it outside the house where it's hot, it starts to heat up that freon starts to expand into a gas. We let it expand into a gas because when things expand into a gas, they're going to release we're going to do all kinds of things. They're going to release some energy, we're going to allow it to cool off, we're going to do all kinds of things. It's called evaporative cooling. It's like what we did with the carbon dioxide the other day, where the carbon dioxide was able to release all kinds of energy when we let it expand, right? So we let it expand back into a gas so that it would release all kinds of energy, and then after it does that, we're going to go ahead and we're going to compress it again. Okay?
So change it back into liquid where it's able to reabsorb that heat energy from the
That's
house.
right. Compress it again, lower its temperature. So it's just the exact opposite. It's called a heat pump, and it's the exact opposite of an engine, a heat engine. But with heat pumps, we don't generally talk about efficiency. We talk about the coefficient of performance. And the coefficient of performance is calculated like this. Coefficient of performance, and this is in horsepower we're using right now. Coefficient of performance in horsepower is the Q hot. Oh, no, sorry, I always say that. It's not in horsepower. They haven't changed the unit itself. It's just for a heat pump. We use HP for horsepower as well, but usually it's a little HP. But you take the Q hot, the hot side, which is the outside of your house, in the case of an air conditioner, you divide it by the work that's being done, or the amount of electricity, power, or I guess the amount of electrical energy that you put into the air conditioning. And this turns out the coefficient of performance is actually the inverse of the efficiency. So where efficiency goes from 0 to 1, right, or 0 to 100% if you calculate it in percent, the coefficient of performance is very different. You take 1 over that stuff, and it goes from the coefficient of performance goes from 1 to whatever, just gets bigger and bigger. And the interesting thing about this is that heat pumps, because they are the reverse of a heat engine, they actually have the highest, they work the best is the better way to say it, they have their highest coefficient of performance when the temperature difference is small between outside and inside, between the hot side and the cold side. So I had a heat pump on my house, but did it work in winter? No, because the temperature difference was so big. It only worked in the fall and the spring, a time which I did not need my heater or my air conditioner. When it's fall and spring, you just let your house be, right? At least I do. My wife likes to heat it up in the fall, because she'll like to cool it off in spring, but she lets heat up in the spring too. But anyway, the point is that heat pumps only work when those temperature differences inside and out are very small. When they get bigger and bigger and bigger, they don't work at all. Whereas,
You have to put more work into it to get it to Fuel is the same level, right?
You have to put in more work, that's correct. So when it's bigger and bigger difference, you have to
So
put
that's
in.
why when it's hotter, your
More
air
work.
conditioning bill is.
That's
more,
correct.
Because you're putting more electricity.
That's right. The hotter and hotter it gets out there, the more and more you have to pump that stuff through and really compress it. And there gets a point where the coefficients the coefficient of performance is so low that you either have to use a different fluid or you have to use multi-stage fluids. If you go to Las Vegas, Nevada, for example, their air conditioners are a little different than ours. A little more powerful. They can handle. They've got multi-stage and they've got. You can cool off. They cool off one end with water and then the other. I mean, it's just the only way to do it. You gotta.
I'm assuming theirs are more expensive, but they're more.
They make so much money in Las Vegas by ripping off people. They don't need to worry about it. There are no taxes in Nevada. Did you know that? No income tax, no any kind of tax. Because there's tax on every single transaction made inside of a casino. There's gambling tax, and they make so much with gambling tax. It's just ridiculous. So anyway, let's do a homework problem. Do the ideal refrigerator problem.
So the best coefficient of performance possible for a
Yep.
hypothetical refrigerator.
Suppose you have an ideal refrigerator that cools an environment to negative 20 degrees Celsius. Heat transfer to another environment. Do that problem. So that, and then and that's it for this one.
Did you say any questions for 15.4?
I don't. Did I?
No.
Which one's for 15.4 did I say?
Steam locomotive. and
The steam
gas-cooled nuclear reactor.
So the steam locomotive one, which was steam locomotives have an efficiency of 17%. See that one?
Okay.
And then we did the one with then the one before it was the gas-cooled nuclear reactor problem. All right. Now we move on to entropy. Entropy is a little bit of a mysterious thing, but it is a result of, or a consequence of the second law of thermodynamics. And it is entropy is a measure of irreversibility of a process. Or in other words, when you do something in the world, when you do some work, apply a force to move something, you expend some energy to change something, you always end up changing things for the worse, you could say. It's like the law of pessimism, okay? The best way to explain it is that you cannot do anything, you cannot accomplish anything without making a little bit of a mess of the universe. That maybe is not the best way to explain it. But this comes from this idea of these cycles that we've been dealing with. These cycles that we've been dealing with on this on these PV diagrams. Let's see if I can find one really quick. Well, it doesn't matter because I got to draw it up on the board anyway. So these cycles always have this loop to them. So here's our PV diagram, V and P. And these cycles always have this loop, so they always end up where they start, supposedly. But the problem is that there's always some area under the curve here. See the area under the curve? What does that area under the curve represent?
Entropy.
Not exactly.
There's disorder, mass, loss, heat, energy.
Yeah. This is lost energy. Okay? This is energy that leaves the system in the form of heat. Now, when we talked about friction before, what did we say about friction when it creates heat? What happens to that heat? It dissipates. And is it recoverable? Hardly at all. And it turns out that everything that you do in the universe causes this kind of loss of energy. Everything. Thinking, reasoning, choosing, even things like that cause a loss of heat energy in your brain, to your skull, outside your hair, and it gets lost. It gets lost in the atmosphere, it gets lost out into space, and it's irrecoverable, which means these processes cannot go around in this loop unless we force them to go around in this loop. Right? We have to have a big reservoir of heat to expand our piston again. We have to have a big reservoir of we have to have a big heat, we have to have a big pump on our air conditioner to compress that liquid again. Right? We have to force these things to go around and around and around. If we don't force them, if we don't have gas in our car to create that hot reservoir, we do not keep our engine going. It does not go on its own. It has to have gas. We have to have electricity to run our, it's a fact of life. Without those things, the heat engine process ends, right? This loss of energy results in a disorder in the universe. It results in molecules that before were organized in the form of matter, in the form of gasoline, electrons that were organized in a wire in the form of electricity, into molecules and atoms that are now wandering around aimlessly with nothing to do, just like 2-year-olds. They don't have any responsibilities, nothing to do, nowhere to go, and they're irrecoverable. They're like lost children in Peter Pan, right? Never get them back. And that is the idea of entropy. The idea of entropy is that every time you do something, you get some of that. And you can only do something if you get some of that. If you don't get some of that, it can't be done. Okay? And the idea is that the entropy of the total entropy or the total disorder in the universe is always increasing. It never decreases if you talk about the total entropy or the total disorder of the universe. It's always getting more and more disorderly, more and more randomized, less and less organized, less and less bound, less and less ordered. Okay? That's the idea of entropy. And it is measurable and it is calculable. Okay? So how do we measure it? How do we calculate it? Well, first of all, we have to give it a letter from the alphabet. We'll call it delta S. That's the change in entropy right here. And for a reversible process, which we just mentioned was illegal and couldn't happen, the change in S is Q over T. Right?
What does that mean then if it's illegal and can't happen?
Reversible processes are the ideal process, and it turns out even they have a change in entropy. Right? So it just means this is just the ideal, just like the Carnot engine is the ideal. You're never going to get any better than this. Right? So it's Q over T is where Q is the heat transfer in a particular process, T is the temperature of that particular process, and you get your delta S. For the total delta S of a Carnot engine, for example, you have Q hot over T hot with a negative in front of it, plus QC over TC. Right? And in a Carnot engine, we say that it's the total change is 0 for a reversible process. But we've said that reversible processes are not, they're not possible. You can get close, but you just can't ever get perfect. Right? So the best you can do, theoretically, is to not have any change in entropy. That's the best change. If you have anything that's less perfect than the Carnot engine, you're going to get a positive change in entropy. The entropy is going up. And what happens as the entropy goes up in the universe? What happens to the universe? What happens? Let's take a tiny little universe. What's that?
Heats up.
Think about what happens when you have things that are randomized, not interacting with each other. What happens to the average velocity out there of things that are randomized? Completely randomized. It zeroes out. So if movement is equal to temperature, and average movement is equal to temperature, and we get to a maximum entropy, maximum randomization, what's going to happen to the temperature? It's actually going to go down, right? They call this the heat death of the universe, and it is the eventual fate of the universe. Eventually, things will become so randomized from processes that are occurring naturally and unnaturally. Eventually, things will become so randomized that the temperature of the universe will approach absolute zero, and everything will just cease to happen. Things will cease to be, right?
That's like trillions of years.
It's a long time from now, but we should be very careful, right? Because, like I said before, everything that we do, has been proven that even making decisions causes the entropy of the universe to go up. Asking questions, right, causes the entropy of the universe to go up. So don't ask stupid questions, right? If you ask a stupid question, then it was a pointless question to ask. The answer that you got was likely as stupid as the question you asked. And then you've increased the entropy of the universe for no purpose, right? So don't ask stupid questions. Save the universe from its heat death. That was the thesis. That was the thesis of one of our papers that we wrote in thermodynamics and physics when I was an undergraduate student. Don't ask. It was stop the heat death of the universe. Don't ask stupid questions. And it was a group paper, and we got an A. It was great.
Does that mean that it would be a really bad idea to continue research on investments to make frogs float?
I don't know. That's pretty important. Making frogs levitate in magnetic fields. So here is calculating the entropy in an irreversible process that is actually, possible to accomplish. We have spontaneous heat transfer is an irreversible process. So something that is cooling off, you have a cup of coffee or something, and it's in front of you, it starts off hot, it cools off. As it cools off, that's not going to spontaneously reverse itself. You're not going to come back to a room that's the same temperature that it was before and find hot coffee just spontaneously got hotter, right? Because it's irreversible. And that is true of all processes in the real world. They are irreversible. Unless you force that thing to heat up again, it's not going to heat up again. So the temperature of the hot side is 600 Kelvin. That's the temperature of our coffee, apparently. Oh, this isn't coffee. This is some hot reservoir. And then we have a cold reservoir at 250. No temperature in either reservoir. And we're going to put something in between them and allow some heat transfer. And we're going to calculate the total change in entropy. The change in entropy is going to be the entropy at the hot side and the entropy at the cold side, and subtract the two. So entropy at the hot side is negative Q hot because the energy is leaving the hot side. So that's the entropy. The entropy is negative Q because the energy is leaving the hot side, or the heat is leaving the hot side, over temperature. Now, if this was the opposite process, the heat was going from the cold to the hot side, like in an air conditioner, then this would be a positive because the energy would be going into the hot side. So you'd put a positive Q in there. But anyway, it's negative because it's leaving the hot side, going to the cold side in a standard process that happens naturally. And so there's the numbers. There's your change in entropy. And I said earlier that energy and entropy are not the same. They aren't, because entropy is not joules. It's measured in joules per Kelvin, or joules over temperature. So it's not exactly energy, but it is related to it. For the cold reservoir, we have energy going into the cold reservoir, so that's a positive Q divided by the temperature of the cold reservoir. We get 16 joules per Kelvin there. And the total is their difference, right? Sorry, the total is their sum, but one of them has a negative on it, so it ends up being a difference. And you get 9.33 joules per Kelvin of change in entropy. And that number should always be positive if it is a natural process. If it's something that you force to happen, then the entropy would actually go down in that region. It would actually be a negative entropy. However, the work that you did to make that happen would cause a bigger change in entropy up. And then you would have an overall change in entropy that goes up in the universe. So, that is entropy. I think I just lost battery in my mouse. Okay, it's been telling me that my batteries were low. So, Let's take a few minutes break, talk amongst yourselves while I get some new batteries for my, are these new batteries? I don't know, I'll check them, find out.
60%
Yeah, it turned it on immediately, so that's a good sign. I'll throw those away so I know they're on. All right, so that's entropy for you. Let's do some problems in entropy somewhere here.
that
But
by covering the house with tarps, we greatly increased the temperature of the house.
yes,
So we contribute massive amounts to entropy.
that's right. We have contributed to the heat death of the universe in a very irresponsible way,
Much more significant than my thinking.
and also working under there to try to build that house. Huge problem. Heat death of the universe is 1 minute closer, or 1 hour closer, maybe even days closer. But there won't be any days by then, so time won't exist anymore, so it won't matter.
As long as it's trillions of years away, I'm cool with that.
Yep, not my problem.
So far, with the sun.
Have you guys ever seen the movie AI? Classic 90s science fiction movie about artificial intelligence, robots, and this genius robot maker makes a child robot. And up to that point, they'd only made adult robots. They'd not made children robots. So he makes this child robot, and it's not well received by, especially by other children, but also by other adults. It's kind of hard for it. So he eventually ends up underwater, and then he ends up getting frozen during an ice age, and then he ends up getting dug out by the race of people who takes over the earth after humans have evolved several times into several other things. And the race that evolves from humans ends up telepathic, telekinetic, really tall with long necks and kind of see-through in their skin. They don't wear clothing. And they have really funky movements. They have floating ships, and they're digging through the ice to figure out what happened to their progenitors. So then they find this little robot, and they reanimate him. Anyway, interesting science fiction movie.
Have you seen the one called Arrival?
I have not seen Arrival. Did we lose Cassidy again? I think we did.
It's about like these 12, they're almost shaped like a three-dimensional thumbnail, or a claw. They land, or not necessarily land, they float around 12 different places around the world, and you can go in there and you can try to communicate with they call it heptatop, because it basically is a giant long tube with 7 legs. And so they try to figure out why they're there by learning their language.
You got a screen.
It's working.
Which movie was that again?
Arrival.
What is it called?
Arrival.
Arrival. No, I haven't seen it. Hello, Cassidy again.
Yeah. Sorry.
That's all right. Just every time it turns off, I'm turning it back on.
Okay.
So did you hear the end of our entropy discussion and the heat death of the universe thing and all that?
Yeah, I mean, I got the gist of it. Chemistry, kind of.
All right.
Chemistry flashbacks.
Yeah, physicists in chemistry treat entropy a little bit differently, and we approach it a little bit differently because in chemistry they treat it very much like it's just to them it's just something you measure, something you calculate, but to us it's philosophical. So here's another interesting way to approach this, and this is where the idea that information, the finding of information, the giving of information, the searching for information, the asking of questions, is actually entropic. It actually does cause entropy it creates entropy and increases the entropy. For example, right here, we have some statistics, right? We're doing the different possibilities of flipping 5 coins And what are the different outcomes you could get? 5 heads, 0 tails, 4 heads, 1 tail, 3 heads, 2 tails, so on and so forth, right? And the problem is that each one of these coins, if it's a different coin, it gives you a lot more options here. So you start to see that there's actually a lot more different things that can happen. Instead of just 1, 2, 3, 4, 5, 6 different things that can happen, there are actually 32 different things that can happen if they were all different coins and you could tell which one was which, right? If they're all the same coin, you can't tell, but there's a lot of different ways these things can happen. And if you increase the number of things that you do, like 100 coins, if you increase the number of decisions you make, in other words, this flipping a coin is just like making a decision. It's just a very simple decision. It's what we call a binary decision. And if you increase it to 100 coins, look at the number of things that can happen. It's into the 10 to the 28 kind of numbers. Number of things that can happen, right? Statistically speaking. Now, if we want to get to a specific occurrence, we want one specific thing to happen. In other words, we're trying to make decisions or ask questions or whatever we're doing to try to get to one particular point. You could liken this to buying the lottery tickets. We're going to buy lottery tickets until we find the one that's a winner. You have a 1 in like 200 million chance. But we're going to buy lottery tickets until we find the one that is the winner. It's not very efficient. You'll never even get it done before the lottery happens. Even if the lottery took a year, if you have a year until the lottery date, you'd have a hard time making that happen. Okay?
You'd have to have $200 million.
Yeah, I mean, it would be a lot of, well, the money is one thing, but just even making the decision for the right numbers. You know, we're talking, and this is so much bigger. 100 coins, trying to find one exact state where certain coins were heads and certain coins were tails. You numbered all your coins, or you covered them all, or you used 100 different coins, and you want this specific state to happen. Difficult. However, what if we could ask a different kind of binary question? That's going to take a lot of work, it's going to take a lot of effort, it's going to create a lot of entropy. However, what if we could ask a different question? What if we knew all the lottery numbers from 1 to 200 million, whatever, and they were just single numbers, not like 53/36/22 or whatever. You know, not picking numbers, but what if we just numbered them from 1 to 200 million? And then we picked the one right in the middle, and we said, is the lottery winning number less than that? That's a much smarter question. Because no matter what the answer is, what have you done to the number of questions you have to ask? You've cut it at least in half, because every time you do this, you're going to cut it in half, right? You've cut it dramatically. And then you do it again. You ask, so let's say that they say, no, it's not less than that. So you know it's greater than that. So you ask, so you pick the number between those, the halfway point and the largest number, and you ask the question again. Is it less than this number? And then you just keep asking, and you're asking the same question, which is easy, right? You're picking a number, which is one choice, and then you're asking a simple question, which is a binary question, yes or no. And that question gives you information. And you cut the number of options in half every time, right? Now, every question can be asked that way, in some way or another. Every question can be asked this way. You can think of a way to cut down the number of possibilities. You can think of a way to simplify the problem that you're trying to solve. And that is beauty. That is logic. That is the idea behind logic and algorithms. If you can ask questions that simplify your system as much as possible every time you ask them, then you are accomplishing great things. And this is all kinds of theoretical. It's all kinds of science. They're doing statistics with it. They're doing psychology with it. And now the science of information is a huge thing. It's its own thing. If you want, have you heard of data mining?
Heard of what?
Data mining.
I think so. Yeah.
People who go out there and on the internet or wherever else, in computer databases or wherever, and they're looking for specific bits of data hidden inside of these huge archives of data. And they're fishing for things. You've heard that term, PHYS, fishing. They're looking for certain information. That's the kind of thing that they're doing. They're using this kind of theory and this kind of philosophy of increasing the entropy of the universe at the smallest amount possible to get your answer. And it is very theoretical. You can calculate equations, you can make models, you can make computer simulations to get the fastest way. What company in the world do you think spends the most money on this right now? Google. What company is the biggest tech company in the world right now? Google. If it's not first, it's second. It's kind of trading places with Apple a lot these days. Okay? They are spending so much time trying to figure this out and do it better and better and better. Increase, increase, increase. And this is where computing is going. Right now, we're kind of at a brick wall as far as making hardware faster than computers. We've not increased the speed of computers for several years by any real amount, except by just adding more and more computer chips to the computer that process parallel. The problem with that is it heats up the computers, so now your computers have big fans in them, so you have to have huge batteries, you have to have a huge computer to do this. And so what they're trying to do is they're trying to create better and better algorithms or better and better computer programs that follow these theories of getting your information in the quickest way possible by asking the fewest number of very high efficiency questions.
I think we talked about that one. I think it was one of the days after class, and we were talking about the missile defense program or something, how it has to be able to work so quickly.
That is correct.
We possess the technology, they just have to make the code
The hardware is there, and that has to do with missiles that are coming in from space are coming in so fast. They're coming in much faster than any rocket could propel them. Much, much faster at a free fall. Talking thousands of meters per second. They're super fast, way faster than the speed of sound. I mean, we're talking 10 times the speed of sound, if not more than that. The fastest thing we've ever built goes like 3 times the speed of sound. So, and the rockets that we're going to intercept them with only go at 3 times the speed of sound. And they're going up from the ground, so they're fighting gravity, whereas the thing coming down from the top is using gravity to make it go faster every millisecond. So it's going faster and faster and faster. The problem with the missiles we have going up is they can't think fast enough. By the time they make a decision, the missile they're trying to hit is past them. And you can say, well, just have them start thinking earlier. Well, the problem is when they'd have to start thinking before they leave the launcher, which means we have to know something about the missile coming in before it's even in range of our radars. So we don't know anything yet. By the time we know anything to give the missile something to think about, it's too late, right? And so that's the problem that they're working on. They're working on making the missiles think faster. One way is to write the software directly into the hardware. That means that every time you make a missile, you are actually wiring up little diodes so that they're thinking through their hardware. The problem with that is that if you want to change it, improve it, or something goes wrong with it, you have to rebuild those electronics by hand. Okay? I mean, each one of those has to be reprinted, rebuilt by hand. So,
an expensive process, I would guess.
Expensive, difficult, it's a great end result if you get it to work, but the end result is not upgradable very easily. I mean, it's just a big pain. So instead of doing that, they build the fastest computer they can and the smallest computer that they can, so that it has very, very short circuits because the traveling of the electrons matters at this point. Even though they travel near the speed of light, that matters because we're moving so quickly at that point. So we create it as small as possible, as fast as possible, and then we create, using these theories, we create algorithms that take as little entropy as possible, that increase the entropy of the universe as little as possible, so that they're the most efficient decision that could possibly be made. And there's a lot of theory behind it, and it's not just some computer programmer that grew up playing video games. It's a guy who took a lot of physics, and it took a lot of statistical mechanics as well, so that they are not only a computer programmer, but a genius of physics and statistical mechanics. And they can figure out these theories and these models and create the best thing possible. And that takes us to the end of 15. We won't do anything else in there in that chapter. So we have just enough time to get us started on chapter 16, and maybe, well, probably won't get into chapter 17 yet, but we'll get started. So, oscillatory motion, that's where we're at here. How many different examples of oscillatory motion can you recognize? Oscillatory means back and forth and back and forth. Can you see in this picture here?
Light, sound from the guitar,
Okay, light. Obviously, he's playing a guitar, so there's sound, which is
The wire.
a vibration. The wire itself, right, of the guitar.
ocean,
Right, the water.
Fire.
The what?
The fire.
Okay, the fire has oscillatory motion, including its light and its heat.
so that's 5.
How about the boat?
The boat has light on it as well.
The boat has light on it as well, but it also will move up and down with the waves along the water. It's probably creating waves behind it as well, right? So there's lots of different signs of oscillatory motion here. If you are familiar with beaches and you look closely here, you can see another one. Beaches often have ripples on them that are the product of waves, either water waves or what other kind of waves? It can be earthquake waves, but usually, unless you're in California, it's not, or Japan. But usually it's water or wind. Yeah. The wind comes up and creates waves in the sand. So they're kind of physical matter, kind of, matter building up on top of matter kind of waves. So lots of different kind of waves, and we're going to study waves in this chapter. We're going to study their properties and some of the science behind them. Of all the chapters in this book, there are hardly any that are more important to a physicist than this chapter. Even though this chapter seems a little easier, it's got a lot of stuff in it, but it's not terribly difficult to figure things out. Even though we don't have a whole lot of vectors and calculations and things that we do, waves are extremely important to physicists. They are everywhere. They are everything. So waves turn out to be quite important, especially to physicists after Einstein. So here's an example of oscillatory motion. Excuse me, you take a plastic ruler and you bend it one way and let it go, and it goes wow, 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 back and forth. It has an equilibrium position, which is where it started before you bent it. It has a maximum position on one side, and it has a maximum position on the other side. And it goes back and forth and changes direction. Where does it change direction in its motion? At the maximum points, right? Where is its fastest speed? At the equilibrium position when it's passing through the middle, right? Does it stop anywhere in its motion? Where does it stop?
Back in the center.
Yeah, it actually stops not at the center, but where it turns around. When you're going from going to the right and then going to the left and then going to the right, you always have to stop to change direction, right? So it actually is at the end points. Now that is something that really confuses people a lot. The equilibrium position is where it has its fastest speed, but during its oscillatory motion, it never stops at the equilibrium position. It stopped there before you bend it, but after you bend it and let it go, it never stops there. It's always either going one way or the other as it passes through that point. That is something to remember, because it's something we always forget as human beings. It's kind of contrary to our internal programming for some reason. We always think this equilibrium position has to be somewhere where it stops. It's actually where it has its maximum speed. Now, is there acceleration in this ruler as it's going back and forth? How do we know?
First, because it turns.
Okay, for something to turn, it has to accelerate. So it goes from going one direction to the left, then it ends up going to the right. So somewhere from going to the left and turning around going to the right, it had to accelerate, right? Where did it accelerate?
The entire. No, the second. The entire.
There's only one place in this whole motion where it's not accelerating. Let me give you that. Where is that one place where it's not accelerating? Right in the middle, right? Right in the middle, it's at its maximum speed and it's done accelerating. But then it starts accelerating again in the opposite direction. When it's moving to the left, which way is it accelerating? To the right. What's happening is it's slowing down and eventually will stop and then turn around and accelerate back towards the middle again. So when it's moving to the left from the equilibrium position, it's accelerating to the right. When it's moving to the right from the equilibrium position, it's accelerating to the left. And if it's at the maximum position on the left and moving back towards the right, which way is it accelerating? To the right again. It's actually speeding up towards the right. And when it's at the maximum position on the right and it's moving towards the left, which way is it accelerating? To the left. Now, if you can keep all those straight, you're good to go. If you can't, try to practice it. There's lots of good explanations in the book. Like, for example, here they talk about the force in this direction when it's here. And of course, the force at the equilibrium is 0 when it's in the middle. The force here, so the forces are in the directions of the accelerations. The velocities, of course, are their own thing. They talk about it a lot in these sections about how this works. And there are a lot of different examples of oscillating systems that follow this. But in most of these cases, you have in all cases of oscillatory motion, you always have some kind of restoring force, which is a force that is always pointing back towards the equilibrium position, no matter where you are. So in the case of this ruler, this restoring force is always pointing either to the left if you're on the left-hand side, or to the right if you're on the left-hand side, or to the right if you're on the left-hand side. It's always pointing back towards the middle or the equilibrium position, called a restoring force. And that's the whole idea. We often use Hooke's law to represent this. Remember Hooke's law from springs and other bendy things? The force is equal to negative k times the distance from the center position, which is x, where k is the spring constant or the springiness of the material. Bigger k means a tougher spring or a more difficult spring to bend. So we often use Hooke's law to describe this restoring force, since it behaves like that a lot, often. So, here is kind of a review example of Hooke's law. We have a car with the suspension system, which are springs on the wheels, and the car compresses the springs 1.2 centimeters when you put an 80 kilogram person in it. We want to calculate the K for those springs, or the spring constant for those springs. So before they get in, we're at x equals 0, or the equilibrium position. It goes down 1.2 centimeters. We're going to convert that into meters, 1.2 times 10 to the minus 2 meters, and it's going to be a negative direction. They're going to call it negative, going down. And then we calculate the amount of force. The amount of force is the weight of the person. So 80 kilograms times 9.8 meters per second squared, 784 newtons of force from that person getting in. Then we use Hooke's law. Force equals negative k times x. We solve it for the spring constant, which we want to know. And we plug in our numbers. Get 6.53 times 10 to the 4 newtons per meter for the spring constant for that spring on that car. Now, we also talked about potential energy stored in a spring, 1/2 kx squared. Well, guess what? That's also the work that a spring does, 1/2 kx squared, so that's going to be helpful to us. And they do a review problem with a gun that has got potential energy stored in a spring that's going to give kinetic energy to a ball, right? And it's going to be a conservation of energy problem where the potential energy equals the kinetic energy, and then they solve for the kinetic energy of the ball, then they solve for the velocity of the ball, and then they get that answer. So that's another review. So everything we've done so far is a review to get us ready for the next section. So let's go to the next section, where we start talking about springs, or we start talking about oscillations. So oscillations are going to have a repetitive cycle. And we're going to want to know some things about this repetitive cycle. The first thing is how often this repetitive cycle repeats itself every second, which we're going to call the frequency. So frequency is measured in cycles per second, and it has units of 1 over time, or 1 over seconds. So frequency is measured in per seconds, or 1 over seconds, and we give that a name. It's called the hertz, named after a good scientist who figured that out. So the hertz. 1 hertz is 1 cycle per second, or 1 over seconds. Those are the units. And if you can count the number of cycles that have passed in a second, then you can just take that number of cycles, divide it by the number of seconds, and calculate the frequency. So here we have a medical imaging device which produces ultrasound by oscillating with a period of 0.400 microseconds. So it tells us the period. Well, they haven't told us what a period is yet. So we got to tell you what a period is. Did they tell us what a period is? Oh, they told us that period is 1 over frequency. So the period of a cycle is how long the cycle takes. If the cycle takes 1 second, its period is 1. If the cycle takes a tenth of a second, its period is 0.1. Right, and so on and so forth. So the period is the inverse of the frequency. So if you know the period, you can just take 1 over that and calculate the frequency. And here they tell us the period is 0.4 microseconds. 0.4 microseconds is 0.4 times 10 to the minus 6 seconds. So we go ahead and plug that in. 1 over 0.4 times 10 to the minus 6 seconds is the frequency. Are you seeing my screen, Cassidy?
Yeah.
Okay, good. So there's your frequency, 2.5 times 10 to the 6, or 2.5 million hertz. We don't usually leave it in that form. Million hertz is megahertz, so that's 2.5 megahertz, right? And 2.5 megahertz is higher than the frequency we can hear. The highest frequency that humans can hear is right around 20,000 hertz, or 220 kilohertz of sound. So this particular sound that's being made by the ultrasound is above the sound we can hear in frequency, so we call it ultrasound, right?
Is it low enough, or is it low enough? Is it high enough?
Can a dog hear it?
Yeah, that's what I was getting at.
I don't know. I don't know what dogs. Every dog is different from what I understand. In there, so every kind of dog hears different ranges of ultrasound. Some of them maybe even can't hear ultrasound. So. But I don't know much about dogs and their frequency bandwidth that they can hear. In part B, though, they ask the frequency. In part B, they say the frequency of middle C in a typical musical instrument is 264 hertz. And we want to know the time for one complete oscillation. So the time for one complete oscillation, use the same equation. Frequency now, 1 over time, solve for the time, the period, and you get 3.79 milliseconds is the time that it takes for one of those waves to complete its oscillation at middle C. And middle C is right about the middle of our hearing range. Middle C is kind of halfway in between the male voice and the female voice as far as speaking goes. And that's why they call it middle C. It's right in the middle of the piano, in the middle of most of your alto instruments. Alto instruments being, well, more tenor instruments, kind of in the middle of the range of tenor instruments, but anyway, it's kind of in the middle of everything, so it's called middle C. Let's see if they got any good problems for us here. I don't like those, those are boring. Let's move to the next section. You guys. All right, so now we're going to talk about simple harmonic motion. Of course, since it's physics, we're going to start out as simple as possible. And the simplest type of oscillatory motion is what we call simple harmonic motion. What it means is that the motion of the object that is going to be oscillating, the displacement of the object or the position of the object, you could think of it as, could be described mathematically using a very simple mathematical function, which is the sine or the cosine. So we think of the equilibrium point as the point where the unstretched spring puts the object. In this case, we have a mass on a spring, and the unstretched spring is at this x equals 0 point when it hasn't been compressed or stretched. To put a mass on the end, we put one of our frictionless surfaces from the physics store underneath it, and then we pull this thing out to some maximum thing, and we let it go. And it goes, and it gets accelerated back towards the equilibrium point, and then it goes past the equilibrium point and compresses the spring to some maximum point on the other side, and then it expands, and then it goes back to the equilibrium point, and then it goes back past the equilibrium point down here, and so on and so forth. Right? It goes back and forth and back and forth and back and forth and back and forth and back and forth, and so on and so forth. So, we're going to do the math for you in a couple of cases here. We're going to calculate the period of this motion. To do this, you've got to do some math that's beyond this class, but the period of this motion for simple harmonic motion is 2 times pi times the square root of the mass over the k spring constant. The frequency is just the inverse of that, so these two equations are quite important. Now there are some kind of rules for this. This motion of it going back and forth from its maximum x to its maximum in the other direction x has to be pretty small compared to the length of the spring for this to work. It can't be so big that you pull the spring out and it overstretches it, for example. It has to be a fairly small movement compared to the length of the spring, even though they're not showing it here. It has to be a small movement so that the spring retains its springiness and everything is cool. And also, there can't be any friction down here, of course, we mentioned that before. But it does have some limitations to it, but that's the simplicity that we're calling simple harmonic motion. So this problem just makes me laugh every time because my older brother had a friend who was his best friend for years who had an old car from the 70s, or maybe even the 60s, that he'd been driving around since he started driving in high school. And he took it with him up to college, and it was just this old green clunker, long hood on it, and the shock absorbers were completely destroyed on it. I don't even know if they were in there anymore. But if they were completely destroyed. And shock absorbers, if you're not aware, are the thing that take the bounce out of the springs in your wheels. You have springs connecting your axles to your car, and if you hit a bump, your car will bounce up and down on those springs forever. Well, not forever, but for like a couple of minutes sometimes if you don't have shock absorbers. And these shock absorbers are just these gas and oil pistons that slow that oscillation down and dampen it so it only maybe goes up and down once or twice, and then it cancels out. Well, it just goes away. His shock absorbers were terrible. So anytime he was about to go on a date and got in his car and got it started up, it always took him a little while to start it up so everybody knew when he was getting ready to go. Everybody would run out to his car and jump on the front bumper and jump up and down as much as they could and get this thing going up and down, almost a foot in each direction. And then he would have to drive down the street and halfway to his date's house with his car bouncing up and down and up and down. And it was just hilarious. So this is the problem that we're doing. We have shock absorbers that are going bad. You'll get some oscillation. And you got this frequency and the period. We're going to calculate the frequency and the period of these oscillations if we have the mass of the car and the K constant for the system, right? So it's just plugging into the problem, plugging into the equation. It's pretty simple. You get a frequency of 1.36 hertz, which is about right, up and down about once every second or so, because that's per second, right? And then a period of 0.738 seconds, 3/4 of a second long period, which makes perfect sense. Okay, now how do we put this simple harmonic motion in with the sine curve and the cosine curve? It's really quite simple. Well, here's the car going up and down. The car that's going up and down as it's going down the street, if you put a pencil on it or a light bulb on it or something and took a picture for a long time, you would see this light going up and down, up and down, up and down across your across the exposed picture. But you can also make what we call a what do they call this? I can't remember. There's a name for this. It's a seismograph if you're measuring earthquakes, but it's not quite like this. But anyway, we have this object that's on a spring here, and it's this mass that's on a spring here, and it's been set into this up and down wave motion next to this piece of rolling paper. It's got a pencil on it, and the pencil is just drawing this wave on paper as it goes by. Right?
Is it like the lie detector test or something?
The lie detector test uses a similar thing, yeah.
Would it be like
except it's not a
polygraph
continuous
or
wave.
something?
So the polygraph uses a similar thing. Yeah. Polygraph measures your voice waves when you're telling the truth and when you're telling a lie. So they measure your voice. They have you tell the truth. They tell you, they say, have you state your name, for example, and whatever else. And then they have you tell some obvious lies. And then they compare those waves to waves of other times when you're telling truth and lies, and try to determine whether you're telling the truth and lies. Now, people are very good liars who can tell the truth and tell the lie with the same amount of stress in their actual mind and in their body can defeat a polygraph test. And so they're not actually great. So how do you defeat a polygraph test if you can't lie?
You lie about everything.
Well, you either lie about everything, but if you have to tell your name at the beginning, I mean, if they know some things that are true about you, then essentially it's a stress tester. So what you do is you give yourself some false stress. You put tacks in your shoe and you step on them when you're telling the truth. And then you step on them when you're telling a lie. And you'll have the same amount of stress in your voice every time. That's literally how you do it. That is probably the most foolproof method of defeating a polygraph test.
They
But,
actually have sensors for your movement stuff.
yep, so they actually put you on a pad now. And if you're moving your feet and other things like this, they put you on a force pad. Then they actually tell you, please don't move your feet. And they might even take your shoes off. They actually do have polygraph testers where you do take your shoes off and you put your feet on metal pads so that they can measure temperature through your feet and other things, because they can measure other things, and they measure, so they can measure all kinds of things. The polygraphs that they have now are very, very advanced, very difficult to beat. But I just thought that was funny because they did that in the Oceans, one of the Oceans movies. You ever seen the Oceans 11, Oceans 12, Oceans 13? Great movies. They're heist movies where these guys are stealing things, and they have one guy has to get a job at a casino, but he's a terrible liar and he's been a thief all of his life. And they ask him, "Have you ever stolen anything?" So he does this, puts tacks in his shoes, and he's stomping. He's like, "Yes, no, no, sorry, I'm just really nervous." It's pretty funny.
Have you seen it's, I think the latest Mission Impossible movie, Rogue Nation, is a part of Benji, the same character who plays Scotty in the new Star Trek movies.
Yeah.
Doing like a polygraph, and he gives all the answers, and he's lying through his teeth the whole time, and then afterwards you just see his little blip,
Yeah.
all the stress going out.
Some people are really good liars. Some people are just really good at it. A lot of practice. Okay. So, we do get this sine curve or this cosine curve, depending on where you start it, right? If you start it so that it's at its equilibrium point at time equals 0, then it's going to be a sine curve, either up or down. So it'll be either a negative sine curve or a positive sine curve. And then if you start it so that it's at a maximum height or maximum depth at time equals 0, you'll get a cosine curve or a negative cosine curve. But either way, you're going to get a cosine curve or a sine curve if this is simple harmonic motion. And that is what defines simple harmonic motion as it is it gives you this sine of this cosine curve. And that's the relationship. And so if it is a cosine curve, this is what the function is going to look like. You're going to get some x. We put it as a capital X because that's the maximum x displacement. And that we call the amplitude of the wave. The amplitude is the maximum displacement from the equilibrium point to the max. So amplitude here times the cosine or the sine times 2 times pi times the time that has actually gone by. So that little t is actually a variable. It's the only variable in this function. And then divided by the period of the wave.
So the capital X is the maximum height, right?
Capital X is the maximum height that the oscillator will reach,
And the amplitude is from like your x-axis up, right?
which is the same as that x.
Okay.
Right. Now, if you want to calculate the velocity of this wave that has this cosine function describing it, then you take a derivative, if you're in calculus. If you're not in calculus, you just take my word for it. And you get negative the velocity maximum, negative the maximum velocity that it would have times the sine of 2 pi t over the period. So that's the function for the velocity. So you have a function for the position of your oscillator, you have a function for the velocity of your oscillator. How do you get the acceleration? Well, you take the second derivative, and it ends up being, it's the acceleration as a function of time ends up equaling negative k times the maximum displacement, which is the amplitude, divided by the mass, which ends up being the maximum acceleration, times the cosine of 2 pi times t over t. So remember that you have a cosine, then you have a negative sign, then you have a negative cosine for these three different functions. And those functions will calculate at any time what an oscillator is doing if you know the period of that oscillator and the maximum amplitude and the mass that's on that oscillator. And this works for oscillators that are simple harmonic oscillators. They have a spring, they have a mass, and those are the only things involved. Okay?
But you don't need the, you only need the mass for the acceleration, right? The other two don't have the mass.
That's correct.
So when you're calculating like the velocity or something along with the simple harmonic motion, are you calculating like it's moving like this, but we want to know its linear velocity?
No, that calculates its velocity within the wave motion. So how fast it's going to its maximum or its minimum or towards the equilibrium.
So you're kind of calculating that velocity from like x-axis to max point?
Yeah, that's correct. It's the transverse velocity of the wave. So it's the linear velocity of, well, and we're not even talking about waves yet. We're just talking about oscillation motion, just back and forth, just a mass going up and down. You know, a wave is something that travels forward in space or sideways in space or something like that. And that velocity is a whole different thing. We'll learn about it later in this chapter.
Okay.
So let's take a look at some of the homework problems we might want to do here. I like this one here. Suppose you attach the object with mass m to a vertical spring. Originally at rest, let it bounce up and down. So I like this one, which is the 1, 2, 3, 4, 5, fifth problem down. You got to do the infant in the bouncy seat. We're going to do the device for the infant in the bouncy seat.
Where's that one?
It's just below the figure 6 with the baby in the picture. So those are your two problems for section whatever we're in. What are we in? 16.3?
Yep.
Okay. Time is it? Okay. I'm going to take a short break, just a few minutes, and we'll come back and do the simple pendulum, which is kind of like the simple harmonic oscillator, but some interesting twists and turns. Just a few minutes. Okay, let's see how much we can get done in the next half an hour, 45 minutes or so. So, the simple pendulum. The simple pendulum goes like this. It has a long massless string with a mass on the end of it. Is anyone listening?
Yes.
So we got a long massless string from our physics store. We got this ball on the end. Now the ball needs to be fairly small. Best if it's a sphere. But the most important part about all this is the mass of the ball must be large compared to the mass of the string, so that the mass of the string is just negligible. And the angle that we pull it out from its equilibrium position is very small compared to the length of the string, or the distance that we pull it out from the center, its equilibrium position is very small compared to the length of the string. Now this is obviously way big. This thing is almost the same length as this. We want it to be at least 10 times smaller distance pulling it away from its equilibrium point as the string is long. So we want that string to be 10 times longer than the movement of our pendulum. Otherwise, we get all kinds of funky things going on, and it's not very simple motion. You've probably seen some of those things that can go on. For example, when you swing a swing really hard, do you ever see the chain bend somewhere in the middle, halfway up, instead of being straight the whole way? It does happen, right? Well, that's not simple motion. That creates all kinds of problems. So for this very simple motion, it's like just pulling the swing back a few inches and just letting it swing back and forth very nicely. Also, the only forces that will be involved will be the force of gravity. That's it. We're going to have no resistance anywhere. We're not going to give it a push. We're just going to pull it back and let it go. So after we let it go, no force but gravity involved. And this is the free body diagram. Well, we do have one other force. What's our other force? No, the tension in the chain, right? The tension in the string right here.
I think it's the T right there, isn't it?
That is. That's the only other force we have involved. I said gravity is the only one. We do have the tension of the string involved. So we have the tension of the string holding us up at the center point up here down to where the ball is, wherever it's at in this motion. Then we have the weight of the ball itself pointing downward straight to the ground. And those are the only two forces, right? If we add those forces together, we get interesting things. If we're out here at this point that is a distance away from the equilibrium point, the tension upward in the string, the part of the tension that's pointing straight up has to equal the tension that's going straight down.
The weight.
Yep. Because it's not moving up or down at that point. It's stopped, right? At that maximum point. However, there is another component to the tension, and that's the one that is going to be pointing towards the center. And so that ends up being our restoring force, right? So the tension ends up having this little extra thing to it, which is nice because then it goes back and forth like we want it to.
So the tension parallels our restoring force?
Yes. Now, if we break these forces into their components, if we break these forces into their components, we get one that ends up being our restoring force, which looks like force equals negative m times g times the sine of theta. Now, what happens when the sine of theta to the sine of theta when theta gets very, very small? Anybody have a calculator out?
Yeah.
Okay, so I want you to plug in the sine of 0.001. What do you get?
Well, really, really small number. To the negative fifth power.
Okay. What happens if you do the sine of 0.00001? So 5 zeros and a 1.
To the negative eighth power.
What happens if you go 0.0000000001?
My calculator is, I'm putting a couple different rows of zeros here. And we get 0.
So the smaller you go in your angle, the closer the sine of the angle and the angle actually become. It turns out they actually approach each other as you get smaller and smaller and smaller. So we can actually approximate this force to be mg times theta instead of mg sine theta. We call it the small angle approximation, and it works both for the sine and for the tangent, since the tangent is just the sine over the cosine, and the cosine goes to 1 as you go to small angles, right? So it works for both the sine and the tangent, and we're using it here for the sine, so that the force that ends up being our restoring force is going to end up being negative m times g times theta instead of m times g times sine theta, which is nice because now we have a very simple equation. That means that the distance that we travel along our arc is just going to be L times theta. Well, that would have been it anyway because that's the definition. L is the length of the string.
Okay.
S is the path along the circle that our thing is traveling on. That's just the definition of radians, right? So we can solve that here for the angle. But we can replace our theta in our mg theta up here with this, S over L, right? And then you get theta equals S over L, or F equals mg times S over L. So the distance along the path that we travel divided by the length of the string times m times g is the restoring force. And it is also 3 constants multiplied by a distance. M times g over L are all constants for our pendulum, right? And S is a distance. So this looks like Hooke's law. So it behaves just like simple harmonic oscillators to a point. You can't pull it out too far, right? Your length of your string needs to be very large compared to the length of the traveling distance of your oscillator. It works for angles less than about 15 degrees in general for longer pendulums. And this is one of the reasons. Have you ever seen a Foucault pendulum? Those big long pendulums with a big huge metal ball, and they're like tracing a path in sand, or they're knocking over little things in science museums.
UNK is a science college, has it?
They have a Foucault pendulum. Most places do. I've been trying to convince them to let me put one in here. We barely have enough height in our ceiling to do it. But not in this ceiling, the one that goes in the stairwell. But that's the reason that they're so long, is so that you get a simple harmonic motion. You want that simple harmonic motion and very good repeatability. But anyway.
I think when I was there talking to one of the professors when I was still looking at colleges, like, it's always constantly moving, but they have a little motor up there.
Yeah, it doesn't move by itself. It definitely has to be driven. Yeah, it would just die off, entropy. So
It comes back.
that's right. Entropy is the death of all things. So anyway, so here you can measure the period of a pendulum, right? So we're going to actually measure the period of a pendulum using the stuff we've learned so far, and then the stuff from a pendulum. But look what happens. If you plug in the K for a pendulum into the period equation we use for a simple harmonic oscillator, the K for a pendulum is mg over L. So if you plug in mg over L in for K here, the masses go away and you just get L over G. So what does that tell you about the pendulum and its mass? Mass doesn't matter. It's just the length of the pendulum that matters. Okay? Now, here is the question of the day. The clock Big Ben. Right? Big Ben has a huge mass on the end of it. Let's take a look at it. What does it look like? That's some movie.
Actually, I think Mass Effect is a video game, isn't it?
I don't know. Here it is. This is what it looks like on the mass in Big Ben. This is a better picture. So it's got its mass on it. You can see one here, but then they've stacked all these little coins and bobs and bits and doodads on it. Why? And notice this other picture has different stacks on it. Why? You can see that this mast has some screws in it and some holes in it and things so that it actually can be moved up and down dramatic amounts. Like it can be moved up and down an inch or whatever. What would that do to the clock?
Slow it down or speed it up.
Slow it down or speed it up. According to the period equation, which one slows it down, which one speeds it up? Let's go take a look at the equation. What happened here? Is this one?
I would say moving it up speeds it up, moving it down slows it down.
Well, let's go take a look at the equation, make sure you're right. Dang it, that's not what I wanted to do. I can't grab my, there we go. So we go back to our book, the simple pendulum. According to our equation, if we make it longer by lowering the mass, it makes the period longer, which slows down the clock, right? If you raise the mass, it makes this L smaller, which makes the period shorter, which speeds up the clock, right? Okay, that's what you said, so that's good. Now let's go back to Big Ben. What are they doing when they start putting things on top of the center?
Increasing its mass.
They're increasing its mass, but we said the mass doesn't matter.
They're also increasing how high up it
They're actually changing the height of the mass, just by a tiny bit. They're just adding a little bit mass on top, so the center of mass of the pendulum bob shifts up slightly, right? So when you're tuning this thing, you want to have a bunch of masses that you can take off on top, right? So you tune it as well as you can by moving the big mass up and down with some masses on top. When you get it there, then you start taking masses off and putting masses on. The smaller the mass that you put on, both in mass and in height, the smaller the adjustment you'll make, right?
is, which is why they have those colors.
That's right, and this is how they adjust Big Ben and other clocks like it. Other old clocks like this from the Renaissance period and from the Dark Ages or whatever you want to call them, whatever they call that now. Those are all tuned using this method of either putting something on top of it or taking something off, and they actually have charts that say if it's off by this much, put this on. But and then it'll tell you in so many days you'll have to take this off and add this because they adjust it all the time.
So, how would you adjust that? Because the pendulum is moving, right?
Well, when it's swinging by, you drop something on it. It's not moving that fast.
Okay.
It's a fairly long pendulum, so its period is pretty big. The height of the tower, that's the length of your pendulum.
Oh, wow.
Yeah. That's why clock towers are so tall. They can also be seen from a great distance when they're tall, but the main reason is so they can have a pendulum, right? You need to have a big pendulum. The longer the pendulum, the more accurate your clock can be.
And since comparatively the tower is a lot taller than it is wide, then you can create the pendulum into a long, tiny angles.
That's correct. Because the longer the pendulum, the shorter the distance it can move, which means you have a better simple harmonic motion, more repeatability. How do they keep it going? That's what all the gear work is up there for. There's some gear work for turning the hands. There's a lot of gear work for turning the hands. But there's a lot of other gear work that actually has masses on it that are pulling down through the gear work and pushing this thing every time it goes to make it keep going. Yes?
What do they do in the
There's
next
three weights that come back and forth on it.
There are weights, some weights that go down. Well, there aren't any weights that go back and forth. There's just one that. There are some clocks that are built with springs in them, with weights that go back and forth, but this one is not that. This one is just weights that go down, and then when they go down a certain, they have several of them. So when one gets down to a certain height below the clock or whatever, then they crank it back up. And they just have to crank them up again. So I think they have electric motors for doing that now. It used to be slaves.
Went back in the day.
That's right. Sanctuary. Well, anyway. Okay, so that's a very interesting thing about the pendulum, though, is that it does not depend on the mass. It depends on the length. The period depends on the length of the thing here. So we've got we've got a simple pendulum that has a length of 75 centimeters and its period is 1.7357 seconds. We want to know what gravity is at that point. Well, here's a way to measure gravity. Because if it's a good simple pendulum, it should have a specific period related to its length, as long as you don't pull it out too far, right? So we solve this equation for the gravity. We square both sides, solve for g, plug in our numbers. We get a gravity of 9.8281. Put that same pendulum on the moon. What's going to happen to it? If the gravity goes down, what happens to your period? If gravity goes down, the period, right, goes up. Because it's inverse. The gravity's in the denominator. So if that number goes down on the moon, then your period increases. So a clock, the same period, the same pendulum on the moon will swing slower back and forth. Right? You can actually also think of the man on the moon who's jumping across the moon, you know, with his big strides. If he's doing the Earth, he's going step, 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 very, very low, very, very small period between these steps. But the same amount of force with a bigger suit on gives him these huge steps with a long period in between them, right? So it's kind of an interesting application. All right.
I don't think we're going to be going back anytime soon. I think Mars is kind of the goal.
We will see. I think they'll probably go to the moon again to test Mars stuff.
Yeah.
To test the Mars rockets, but
I feel
besides
like
that.
we're gonna go to the moon to test some things first, so we have different gravity and different atmosphere.
I think the most likely option for testing would be things like their environment. See how that looks.
Okay, so let's see here.
I think after the movie The Martian, we'll be like building everything the way the specs and maybe a big satellite. Well, we are 730 days, 60 days. We're tracking somebody closing that thing. It's not
Let's do the one where you change the length of a clock's pendulum by 1% exactly at noon.
This is for homework,
Yeah.
and we are on 16.4. We're doing the one where you change the length of a pendulum on the moon.
Yeah. And figure out what time it will read 24 hours later. This is kind of a challenging question. I'm not going to give you any clues. But that's the only question I'm going to give you from there. What time is it? We've still got time. All right, let's talk about energy. See, it's all just review now. You know what energy is. You even know what the energy is in a spring, 1/2 k times x squared, right? Where x is the displacement from the center. So that is, if it's at its maximum, that's the amplitude, right? But you also know that that something that's oscillating, going back and forth, has some kinetic energy when it's not at its maximum amplitude. So the kinetic energy of the oscillator plus the potential energy of the oscillator at any given point has to be constant. At any given point, if you stop the oscillator right there in, freeze time for a second, then the kinetic energy plus the potential energy, the spring potential energy, at that point is the same as it is at any other point. When it's at its maximum displacement, it's all potential energy. When it's right in the middle at equilibrium, it's all kinetic energy. Right? But it has to be constant. If you're talking about the functions that we use for displacement and velocity, we start thinking in terms of sines and cosines, and we start thinking in terms of radians. And so we make a conversion to angular. So this is for an angular oscillator, essentially. So for an angular oscillator, or one that moves on a circle, which is like a pendulum. Pendulums move on a circle, right? Then it's 1/2 times the mass times the length squared times omega squared, where omega is the angular velocity. and then 1/2, and that right there is your kinetic energy. And then your potential energy is 1/2 mgl times theta squared, where the theta is the angle away from the equilibrium angle.
So,
So you have
I
it
thought
for
was
now.
mg over L, so how does it become mgl when you plug that in?
What's that?
I thought the K was mg divided by L, so how does the L become multiplied by?
That's little k, not big K. That's K, the spring constant, K for force. This is for velocity.
Oh, okay, gotcha.
We made the velocity, the tangential velocity is equal to the radius times omega, and the radius is the length of our string, right? So
So the K, spring constant.
the K is plugged in over here.
mgl. Okay.
Okay, so there you got, now you've got conservation of energy equations for simple harmonic oscillator and your simple pendulum, and you're good to go. The interesting thing is that you can solve this equation for velocity, and you can get the maximum velocity equals the square root of the K constant over m times your maximum displacement.
K is in the spring constant, right?
Yes. Useful equation. Also, you can get the velocity at any point if you know the velocity max, and you multiply this by this 1 minus your position divided by the maximum displacement. Very interesting solution, I think. But you can also get this in a similar way for the maximum angular velocity of a pendulum, equaling the square root of g over L times the maximum angle. So the maximum speed on an oscillating road, so the maximum speed of oscillation on a bumpy road, right? You have a 900 kilogram car, you've got a mass, you've got a force constant in the springs. It hits a bump and bounces with this amplitude. We want to know the maximum vertical velocity if no damping occurs. Well, you just solve it. Plug it in, crank it out, 0.852 meters per second. It's kind of important because you don't want a car to accelerate you too much, right? It's very uncomfortable, very jerky. And sports cars are much jerkier than, sedans or family cars. They have much different springs in them because they have to absorb that force much more quickly. They have very little bouncing room, right, in their suspensions. So sports cars tend to be a rougher ride, just all there is to it. Unless you're talking, most American sports cars don't have a rough ride, unless you're talking like the Corvette. Most American sports cars are fairly high off the ground, and so they have a lot of room to bounce a lot. You talk to, I don't know, the Camaro, just about everything, the Challenger, the Ford Mustang, all those American sports cars are very high off the ground, except for the Corvette and maybe like the Dodge Viper. They're the ones that are only 2.5 feet off the ground. They have almost no room, very uncomfortable, every little bounce you feel. There's just no room to put in a spring that gives that much. So that's the trade-off. Yep.
Shortly after we started this class, and we moved Fast and Furious, the first one.
Yeah.
It was partly like hop over some train tracks, and when we come down, the car goes from about there to there because it's going.
Yeah. Yeah, cars that are built for road driving do not make good sports cars no matter what you do. There's no way to modify a normal car to make it into a great sports car or racing car no matter what you do. They're just built all wrong. And people say, well, what about stock car racing? There's nothing stock about a stock car. Absolutely zero. Nothing at all, except that they all start with the same rules and they all bend them. That's really the only thing that's stock about stock car racing. They change everything from race to race, sometimes from lap to lap in those cars. And they are designed to do amazing things. But race cars designed for racing are never designed for comfort. They are not, and that's one of the reasons that racing cars is so difficult. It is difficult to drive a car that is bouncing. And cars that are race cars bounce. They bounce the driver around a lot. They keep the wheels on the road pretty well, but the driver gets jerked around a lot. And it's very taxing on the driver. It causes them a lot of injuries, a lot of small injuries, and it makes them really tired. They're extremely tired. It's just a really hard thing to do. It's not easy. It's not just driving like driving a tricked out Toyota or something. It's a very different deal. So anyway, problems here. Not really liking those problems. Kind of not helpful. Okay, let's do this engineering application because I really like this one. Tall buildings are like huge rubber bands. They're like big rubber statues. They actually oscillate all the time. They're always wiggling back and forth. And how many of you have ever been in a building higher than 30 stories? No, nobody, no. You've been in higher. Where did you go? Chicago or New York? In Las Vegas. Okay, so there are a lot of buildings in Vegas, New York, Chicago. You pretty much have to be in one of these bigger cities to see this. First time I was in a building that was over 30 stories, I was in the Transamerica building in San Francisco. I was on the top floor, 40 stories up, 40-something stories up. That's the big pyramid building there in San Francisco, the tall, pointy pyramid building in San Francisco. But it's no longer the tallest building in San Francisco. It used to be. But you can feel it up there, especially in a windy place. You can feel the building moving and oscillating. Could you feel it when you were up there? Yeah, it's kind of weird. It's freaking. Some people get sick, especially when you're in like a rotating restaurant on the top. Because there's another hotel that has a rotating restaurant in San Francisco on top of it. Yeah, there's one in Las Vegas as well. And then you have the shaking and the rotating, and then you have people throwing up. It's a bad place for a restaurant. So anyway, the point is that you can actually dampen that. And the way that you dampen that is you put a very large oscillator up there with a huge mass. So when the building tries to shift, the oscillator shifts the other direction and dampens it. It's kind of like the shock absorbers in your car, but it has to be pretty big. So here we have this Citicorp building, a Citigroup building in New York City. The object is on this mass of 4 × 10 to the 5th kilograms on springs. Let's see what kind of solution they give us. They just give us the answer, so that's great. It's going to dampen these wind-driven oscillations. At the same frequency the building is being driven. Oscillates so they're telling you the period of the oscillations, and then they're talking about energy there. So I'm going to change the numbers in this really quick, so get your pencils out. Instead of having an object with mass of 4 × 10 to the 5th, we're going to have that be 2.5 × 10 to the 5th. And then everything else can stay the same. Okay, so in this section we're going to show how uniform circular motion, remember the ball going around and around the merry-go-round? Or whatever, the kid going around and around the merry-go-round. That simple circular motion, at a constant angular velocity, is related to simple harmonic motion. So here is the apparatus we're going to use. We got this ball or this light on this wheel that's going to go around and around at this constant velocity, and we've got these lights above it that are going to shine down and show us the shadow of the ball on the ground down here. And when we do that, and if we do that on a piece of sliding paper, we see that we do get a sine/cosine type of curve. However, is it really a sine or cosine? And that requires us to do some math. So we do some math. This should look familiar. We've got our circle with our radius. We've got our x component. We've got our radius here, which is the capital X, which is going to be our maximum amplitude. Because the maximum distance the ball could get away from the center would be when it's pointing straight up and the lights are coming from this side. So this is our capital X, which is our amplitude. But the actual X that we're going to see is going to be this one here. It's going to be the y projection or the x, they're using the x projection. Whatever, it's going to be one of these projections, one of these components of this vector going from the center out to the point where the ball is. And when you do the math, you end up with an x equals amplitude times cosine theta, and x equals amplitude times cosine omega t when you relate the distance in angle is equal to the angular velocity times time. And then the angular velocity is equal to 2 pi over t here. It turns out because 2 pi is the total distance around the circle, and the t is the period or the time it takes to get around the circle. So that is the angular velocity, right? The distance divided by the time. And then, where this is for a unit circle, so the radius is 1. And then you get this equation here that says that the position is equal to cosine times the cosine of 2 pi times the time divided by the period. And if it's a different radius, that x you just multiply that x out in front and you're good to go. Because everything in here is equal to a maximum of 1. Right? So it's actually a really interesting way to develop this is the same equation that we got at the very beginning of the chapter, but now we're showing you a mathematical way to get there, an algebraic and trigonometric way to get there rather than calculus. But it does relate to this circular motion. And if you go through all the math that we did before, you'll find the same answers for the period, the same answers for the velocity max. You'll get everything that we did before going from a different direction mathematically and theoretically. But it does show that circular motion and simple harmonic motion are related to each other directly. No homework there. Okay, 16.7, damped harmonic motion, resonance. 10. Okay, let's stop here because this stuff is going to be all related to each other. We'll get on to that later, and then we'll move on to chapter 17, and then we'll be done.
I have a question about the lab.
The last lab?
Yeah, Bernoulli's.
Okay.
So I did my experiment and I made my chart that just like they have.
Yep.
So when I'm calculating the drain time, do I use that equation of the time drain it's on the bottom right?
Yes.
Okay, my numbers were like way off from my drain time that I calculated is pretty off from what actually happened.
How far off?
Well, I just didn't even, I think, like for my first one, I got like 17.4 seconds was what I measured, and what I calculated was like 6 seconds or something.
That is far off. Did you measure? So whatever bottle you used, did you make a good measurement of the radius there? Diameter of that bottle?
The diameter, see, the thing is, I think, well, I didn't get the diameter of the bottle yet. And so I just tried like guessing, and maybe that was my problem.
Yeah, that will definitely cause some issues.
Because I wasn't home at the time I did my lab, and then I had to leave.
Yeah,
And I don't know
definitely.
what.
Definitely guessing on those diameters is going to cause some issues in that equation because they're kind of important.
Yeah, and I ended up only using like 20, or instead of using 20 centimeters of water, I only used 10.
So and there's a place for that in the equation that you can plug in as well. So.
Right, and I had to convert from inches because I was using a drill bit with inches.
Yep, and that will cause a little bit of error, but it shouldn't cause a big one if you just get a good measurement. So.
And my numbers were pretty close up until like my last one, the smallest one I did. The first three were only like 1 to 2 seconds different from each other.
Well, and the smallest one will cause issues as well. So how small was your smallest one?
It was 5 30 seconds.
So about a quarter, 5 seconds, less than a quarter of an inch. So once you get down to less than a quarter of an inch, you get some turbulence as well. So if you're within a couple of seconds at the beginning, you're pretty close, and that's fine. But at the end, when you start getting turbulence, it creates a lot of backup, so your time would be much longer. And is that what you saw?
Yeah, like
Yeah.
it was 30 seconds more than the other ones.
Yeah.
The other ones were pretty close in.
Yeah,
Like-
that is most likely your problem is that hole was just too small. So
Alright, and so all I send you is the chart.
what you're going to do is you're going to write a one-page paper describing what you did to show that their experiment was good or not good, because they did the experiment and wrote this paper. So you're going to write a response to their paper essentially, and you're going to say, I did this same experiment. This is how I did it, because there are going to be some differences, and I showed that your results were valid or not valid, and by how much. So it's like you're being a real scientist now. You're actually responding to another scientist's results with your own results. This is what scientists do.
Okay, so is it going to be double spaced, or is it just one page?
You can space and a half it if you want. Single space or space and a half is fine. Don't go as far as double. But usually science papers are single spaced. So and they're usually 12 font single spaced. You can put in images of diagrams of your experiment. Just don't make them too big. Make them big enough to see clearly, but not so big that they're taking up the whole page. Kind of thing.
Oh my goodness, I don't even think I could draw mine. We ended up using my mom's painter's tools, and
You don't- You don't have to draw any details. You don't have to draw the details of what was holding things up or anything like that. Just where the bottle was and what any scientific instruments were, and label any heights and distances and diameters and that kind of thing. So if you want to do that, you don't have to. So
Okay.
any other questions?
No, I think we're good. Thank
Okay,
you.
we'll see you later.
Bye. Oh, could I actually, could one of the, Andrew or someone send me the questions he wrote down just so I can double check that I have all of them?
Sure.
Okay.
Yes, I'll have them send that.
Okay. Have a great day.
See you later. Okay, Andrew, do you mind sending me an email of the questions for the homework so I can send them to Cassie?
Yeah, I can do that.
Thank you.